Okay, let's get started. Today we are going to talk about binary search. And homework 4 was due today, and homework 5 was out today. And regarding midterm, I would like to talk about it once again. The schedule is on April 16th from 1 p.m. to 3 p.m. And you will need to take midterm, not in this room, but at Building C in room 104. And the coverage is from Python primer to binary search, today's class. And it includes lecture slides, codes, homework problems, and you don't need to worry about those optional problems. And it also includes recitation materials. And the format, the problem format, are as follows. We have 3 types of midterm problem formats. WWPP, what would Python print? And PPP exercises, similar to what I gave you during class. And short answer questions. And it is closed book, closed laptop, so don't bring anything but your pen and eraser. And don't forget to bring your student ID card. And next class is going to be a review class. It is basically a Q&A session. You can ask any questions regarding lecture materials. It is optional. I'll just accept questions. So if you don't have any specific questions, then you don't need to attend this class. And you can ask in Korean. I'll communicate in Korean as well. But if you ask in English, of course, I will answer in English. And regarding homework problems, if you have any questions, please refer to TA. All right, up to this point, any questions regarding course logistics? All right, last time we talked about applications of queues, and we left from one PPP exercise from last class. We'll start from here. The last PPP exercise from last class was opening lock. And we have 2 inputs. The first one was dead end. If we reach this point, the lock is closed, the lock is broken, and we cannot go further from this point. And the target is what we want to reach. And we're going to start from 4 zeros and then tick one spot at a time. So for example, if you tick the first position, then it could become 9 or 1 according to the direction you choose. And the goal of this function is to print out the minimum number of ticks or rotations you need to perform to reach this target. Okay? So to solve this problem, we're going to use queue. So we'll first make a queue. And then in this queue, we're going to enqueue a tuple. What we are inputting here is the current state. The current state is 4 zeros. And in addition to the current state, we're going to add the number of steps. So every time we pop or dequeue from this queue, we're going to increase this number of steps. Okay? So this is the initial state. And we're going to keep track of the visited states. So first, the 4-0 state is what we've visited. In the later of this class, to keep track of visited, you would like to make a set rather than this list. So if you already know what a set is, then you could use set here. But even though you don't know set, it's okay to use list. Okay, then what we are going to do is like this. While our queue contains some items, we're going to dequeue the string and step. So from this queue, we're going to dequeue one item. So why are we using queue here? Because we need to keep track of the minimum state, minimum number of rotations we need to perform. So the smaller ones that goes into this queue first should get out of this queue for the first time, okay? So that is why we are using queue rather than stack. So we cannot use stack here. And after that, we are going to check whether this string is dead ends. If that happens, we need to just go to the next iteration. And if this string matches the target, then we're going to just return this step because we already reached our target. And this is the tricky part. We are going to tick each position. So it's 0, 0, 0, 0. But we can choose to change the first position or the second, third, or fourth. So we are going to change all these positions step by step and then check whether we can reach the target. So what I mean by this is we're going to retrieve the string at the position I. And we are changing I from 0 to 4, 0 to 3. So we're going to inspect each position. And for each position, we're going to tick it into two directions. So if we tick this first position into one direction, it's going to become 1. And on the other direction, it's going to become 9. I explained this in the last class. So we retrieve the number at the ith position. And we're going to tick this number into two directions. And how can you do that? How we are going to add this dx to this number. So if it was 3, then it could become 2 or 4, according to the direction we tick it or rotate it. However, you need to be careful about this because when this number is 0 and we subtract 1 from 0, it becomes -1. However, in our log, there is no -1. It should become 9. And to handle that, we're going to perform this percent operation to get the remainder. And by performing this percent operation, 0 becomes 9 or 1. Okay? So you need to be careful about this percent operation, modulo operation. And after that, we're going to construct new string. And this new string is going to be up to I, we're going to use the same number. And we're going to add this new number we've created. And we are going to add the remainder number from I plus 1 to the end. Okay? And if this string new is not visited, we have not visited this string, then we're going to add this number to our queue. However, here we add this number and the step size incremented 1 because we already took 1 step here. So the next step takes 1 more step than the current one. So that is why we are adding 1 here. So as you can see here, as this loop goes around, this step size increases 1 by 1. And to this visited list or set, we are going to append this string new. So afterward, if we reach this point again, we are not going to search this direction any longer because we already inspected this string new. And after inspecting all possible combinations and directions. If we cannot reach the target because of these dead ends, then we're going to just return -1, meaning that we cannot reach the target. Okay, any questions regarding this problem? All right, let's move on. And today's main topic is searching. What is searching? Searching is the process of looking up data in our stored dictionary or list or anything. Up to this point, we've implemented some containers like list, array, queues, and stacks. For example, you might want to look up a person in the telephone book. Nowadays, we don't use telephone book. However, your smartphones still keep your telephone book. And we sometimes search for the meaning of a word in a dictionary. Although you did this using digital dictionary rather than paper dictionary. And Python lists have a method called index. And this one returns the index of the first element that is equal to this x. And if the elements of the list are in no known order, then what we can do is just sequential search. And this is sometimes called linear search. And what does linear search mean? Let's implement this and think about the meaning of linear search together. So linear search is very simple. This A is a given array, and X is the item of interest we want to find inside this array. And what this linear search is doing is just inspect every element in this array. That's all. So we change the index from 0 to the end and check whether the current item equals to the given X. If that happens, we just return that index. Otherwise, we are going to raise a value error, meaning that we don't have X in this array. Okay, so it's very simple. So it's basically inspecting all the items inside this array. And in general, the complexity of this linear search is O(n). Here, n means the number of items inside this array. Why is this so? Because we need to inspect all the items. And can you do better? It is often possible to improve this in practice by keeping often needed elements at the front of the list. So if the elements are randomly ordered in this array, then there's nothing we can do about it. The only thing we can do is linear search. However, in some way, if we order the items when we are storing the given elements, then we can do better than this linear search. And if that is the case, the best case could become O(1). And we're going to talk about how we can make it O(1) in the later of this class. All right. Then what about searching in sorted cases? Given a list A with a non-decreasing sequence of integers, meaning that there could be some items with the same values. That is why I'm saying non-decreasing rather than decreasing or increasing. If that is the case, then we can just stop as soon as we find the item. So this is the case of sorted linear search. Let's have a look at the code together, line by line. So in the case of sorted linear search, what we are going to do is similar to what we did for linear search. We are going to inspect all the items inside this array. But if this item at the index I is larger than or equal to X, then we'll just return I. Otherwise, we're going to return length of A. The purpose of this sorted linear search is somewhat different from linear search. In the case of linear search, the aim of what we aim for is finding the item X. However, in the case of this sorted linear search, what we are aiming is to find the position where to put this X. So if X is larger than any element in this array, meaning that we reach this line, then it returns length A, and that becomes the position of X. Okay, so that is what we do for sorted linear search. That was sorted linear search. So if X is not in the list A, what we are going to do is just return the position where this X should be inserted. So that is the purpose of sorted linear search. And this is today's main topic, binary search. In the case where the data of a list is sorted, I told you that if data is not sorted, then there's nothing we can do about it. But the only thing we can do is linear search. We compare the item of interest with the middle element and search in the left half or the right half. So we are dividing the space into half at every iteration. And the most intuitive implementation is using recursion. And we are making binary decision in every step. So this is the illustration of binary search. In the case of sequential search, let's say we want to find 37. Then it should go from the beginning to the end, and we take just one step. So we are reducing the search space one by one. However, in the case of binary search, we go to the middle like this, and this value is smaller than 37. Then we just remove this half, then go to the right half like this. So in this way, in every step, we are reducing the search space by half in every step. And as you can imagine, this binary search is much more efficient than sequential search. And in the best case, where the item of interest is at the middle, then the step it takes is only one. But in the case of sequential search, it takes 8 steps. And if the binary search happens in the worst case, then it takes 4 steps. Let's say the item of interest is 1. Okay, in that case, we go to the middle and go to left half and go to left half again. So it takes like 4 steps. On the other hand, the sequential search takes only 1 step. in this case. So binary search, in the worst case, it only takes 4 steps. Okay, from now on, we are going to implement binary search. But before we actually implement binary search, I want to share one fun fact about binary search. The binary search was first published in 1947. And the first implementation without bug did not appear until 1962. As you can see here, the idea is quite simple. We just divide the whole array into half and go to right half or left half by making binary decision in every step. However, this simple problem or program took quite a lot of time to implement without any bug. And in an experiment, professional programmers were given ample time, enough time. And only 10% of them could get this small program right. Okay, so even though this might look very simple, you need to be very careful when you're implementing binary search. And in other concepts, programs, the index, the mistakes in making or writing the index could be just nothing, or the effect of misusing index could be minimal. However, in the case of binary search, if you make a mistake in writing the index, then the ramification could be huge. So you need to be very careful about the indices. All right, let's implement binary search together. Because our binary search takes the same input, the array of interest, the array we're going to inspect, and the item we want to find inside this array. And here we're going to define another function, findDirect, because we need to define the boundaries. And at the beginning, we're going to inspect from the beginning to the end. So we're going to pass these two values. The first value is the left boundary, and the next value is the right boundary. So we're searching all the items inside these two, specified by these two indices. And we're going to define find recursion. Here, A is the array, X is the item of interest, and I is the left boundary, and J is the right boundary. And as we go on, we're going to reduce these boundaries. And by doing so, we can reduce the search space. We first need to define the base case. If J is smaller than I, then we're going to just return I. That is our base case. And after that, what we're going to do is define the middle index. We're going to take the average between these two boundaries, the left boundary and the right boundary, and take the average. And if this value at the middle is smaller than X, what we are going to do is we're going to find the right half. Otherwise, we're going to return this one, and this one corresponds to left half. Okay, so this is basically how we define binary search. When you look at this is quite simple. Here I'm checking only this base case. However, if you wanna add more expressions, then you could also check if a mid equals x, then you can just return mid. You can add this part. However, even though you don't add this part, it works perfectly. So this is optional.
저희 지금 대열의 원수가 전부 다른 경우 가져가는 건가?
Sorry?
대열의 원수가 전부 다른 경우.
Yeah, everything should be different. Okay. And I mentioned that using recursion sometimes overflow our stack memory. And we sometimes need to we better use iteration rather than recursion. And this is going to be our first PPP exercise. Think about how you can turn this recursive binary search into iteration. Okay, this is our first PPP exercise of today. Before you tackle this problem, please send me a PPP message using the Zoom. I'll give it one more minute. Okay, thank you for sharing your answers. Let's do this together. When we turn a recursive function into iteration, we need to first define variables which are changing over time. Here, what are changing? I and j are changing over time. So here, I was originally I, however, here it becomes mid plus 1. And in the other case, j becomes mid minus 1. So I and j are changing over time. And the initial value of I and j are as follows. The beginning of this array and the end of this array. And the condition of running this recursion was when this condition is not met. So we are going to reverse this condition. And what is the condition is? While j is larger than or equal to I. So that is the opposite of this condition. So be careful about this equal sign. If that happens, then we're going to calculate mid as before. And we follow this process again. If this mid value is smaller than x, then we are going to change I as mid plus 1. Otherwise, we're going to change j as mid minus 1. And after this iteration is over, we're going to return I. That's how we turn this recursion into iteration. And as I told you before we go down here, we can check if a mid equals x or not. And we can return mid here. That is also possible. That is up to you. Okay. I'll give you the test code. In this class collab. And after class, you can run it on your own. So you can compare the performances between just linear search, Python search, and binary search. So if you run this performance comparison result, then you can check it on your own. But I'll just show you the result of running this code. When we make a very, very large list and try to find an item inside that list, Python search, the default index method, takes like this amount of time. And linear search takes longer than Python search. And as you can see here, Python search is doing some optimization than the naive linear search. And when we perform sorted linear search, the performance is not that different. However, if you perform binary search recursive, then it takes only 6 microseconds. And when you turn this recursion into iteration, you can get even better performance like this. So this is what binary search is about. As you can see here, the concept of binary search is quite straightforward. And we are going to see some applications. I'll give you some PPP exercises. The first problem is implementing power xn. This one calculates x raised to the power of n. So when you call 2 to the power of 10, it becomes 10,024. And it also supports decimal numbers like this. And in the case of power, you can perform minus power like this. Try to implement this pow function using binary search. As usual, please send me a PPP message before you tackle this problem. I'll give it 1 more minute. All right, let's solve this problem together. Thank you for sharing your answers. Um, the naive solution might look like this. This one takes O n in the case of naive solution. We first initialize result as 1 and I, the number of powers or iterations or the number of multiplication as I. And while I is smaller than n, we are going to multiply x to the result. And we increase I by 1. And then we return result. So this is first naive solution. I where it takes O n. And how can you make this better? Achieving O log n complexity. I haven't mentioned this, but binary search takes log n complexity. And what we can do is like this. We first need to think about the base case. When n equals 0, then we need to return 1. And if n equals 1, then we need to return x. And if n is smaller than 0, then what we can do is return 1 divided by power of x minus n. This is the definition of negative power. In other cases, what we are going to do is divide this power into half, like this. So we are calculating x to the power of n divided by 2. And if this n is an even number, then we are going to return division by division. Otherwise, we are going to return division times x. So this is for when n is even. This is when n is odd. Okay, so this is how we implement PAL. And I'm going to give you a similar problem to this one. So maybe because this is your first time applying binary search or binary decision paradigm to problems, this might look somewhat tricky at first. The second problem is as follows. This one is actually from Microsoft and VMware coding test. Here, propose is to implement a square custom. This is similar to what square root is. However, when you take square root of 8, it is 2 something. So here, we are removing this decimal part. That's what this square root custom is returning. Okay. Try to implement this square root custom using similar paradigm like this. Okay. And as usual, before you tackle this problem, please send me a PPP message.
음, 그 이거인데 저 위에 번세고 문제에서 저기서 어떤 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 부분이 음, 이게 어떻게 말이야 그 이벤트 한국과 유사한지
터치 스페이스 이렇게 반으로 줄여가고 있잖아.
음, 음, 그거는 그거는 인덱스를 찾기보다 그냥 분할 정보에 들어간 거 아닌가요? 인덱스 찾기보다
뭐 관점의 차이죠. 이것도 그러면 분할 정보라고 볼 수 있지 않나요?
네. 이건 굉장히 또 분할 정보인데 저희들 인덱스 찾는다고 보기가 어려우니까 분할 정보 맞는데 이분 선생이 아닌 것 같다.
그렇게 생각하셔도 돼요. 네. 당연히 그렇게 생각해도 되고 여러 관점을 가질 수 있으니까 그거는 당연히 괜찮습니다. Okay, let's solve this problem together. Um, I'll just show you one knife solution first. That is initializing n as 1 and m as 2. And we can perform n times n and check whether this value is smaller than x. And if m times m is larger than x, then we can just return n. Otherwise, we are going to increment n by n, m by 1, and m by 1. So this is one way of solving this problem. However, this is a linear search of finding the square custom. And this is not efficient. And what we can do, rather than doing linear search, is define two boundaries, because custom square root might be between 0 and x. So we are going to say the low is 0 and high is x. But before then, we can define some special cases. When x equals 0, then we need to return 0. And if x equals 1, we can return 1. However, I haven't specified whether s could be 0 or 1 or minus. I haven't specified this. So you can ignore this part. All right, then what we are going to do is, while this low value is smaller than or equal to high, we are going to divide the search space between 0 and x into half. So we are going to find the mid value. However, this mid value should be between low and high. So we need to take low plus high minus low divided by 2. And if this mid square is larger than x, then we are going to change high as mid minus 1. Else if this mid square is smaller than x, then we are going to change low as mid plus 1. Otherwise, we're going to return mid. And after all this, if this iteration is over, then we're going to return high. Because after a while loop is over, that means low is no longer smaller than or equal to high, but low is larger than high. So that's why we're returning high at the end. So this is one way of implementing square root custom. If you can solve this problem in other ways, but that is also efficient, then it is okay. Okay, that was our second question. And I'm going to give you third question. This is also from a coding test from Adobe. Here, we want to find the target. However, in this case, the numbers could be possibly rotated. So what I mean by rotation is like this. The input numbers could be like from 1 to 10. But at some point, let's say this is rotated at this point between 6 and 7. Then these numbers as a set goes to the front. Other than that, the order remains the same. So this is what I mean by rotation. 9 and 10, two elements could be rotated like this. Anything is possible. So when that happens, these numbers could be possibly rotated, or it may not be rotated, but it's just a normal ordered number of lists like this. If that is the case, and we want to find target in this nums array or list, then how should you implement or modify the binary search we've learned? You also need to take O log n. It should be as efficient as normal ordinary binary search. This problem might look somewhat tricky at first, so I'll give you some hint. One way to solve this problem is as follows. You can just modify the basic binary search. And what you need to do is just changing the criteria. And we first need to come up with some criteria. And the main point of this problem is designing this criteria. So you need to design this criteria. So that is the main focus of this problem. And when you're designing this criteria, you need to think about two cases, two criteria. The first one is to check where the rotation center is. So what I mean by rotation center is, let's say 7, 8, 9, 10 goes to the front. Then rotation center is here. You first need to determine whether this rotation center is on the left side or right side. And depending on the location of rotation center, you need to check, you can decide whether to look at the left half or the right half. Okay, so that is the first criteria you need to design to check where the rotation center is. And the second criteria you need to come up with is to determine where to look at. Left half or right half. Okay, so you need to think about two criteria. And after you determine these two checkpoints, everything else is similar to binary search, basic binary search. You just need to go to the left half or right half. So when you first look at this problem, this might be somewhat confusing. However, try to draw many examples when the rotation center is left or when the rotation center is right, and try to think about different numbers for target. Then you may be able to write this code. Okay, I guess it would take more than 5 minutes to solve these problems. So let's just call it a day and start from here next class. All right, thank you for your participation. If you have any if you have any questions, I'll just stick you around so you can come to me and ask questions.